So we need to think about the things that are going to affect the reading on the scale, aka the normal force. What's going to affect the normal force in this scenario and make it different? The impulse. The impulse of the sand hitting the bottom, right? So we know that this, we'll call it just the impulsive force. The sand changing its momentum. And what else? What else is going to change the reading on the scale?
Sand and free fall.
No. Change it from when there's no sand falling. What? Yeah, the sand in free fall. How much weight is being, how much of the weight of the sand is being led by the normal force? None of it. Normal force is a reaction to something pressing down on it. None of the sand in free fall is pressing down on it. So we know that mg of the sand in free fall is going to reduce the normal force. And the impulse force of the sand hitting the bottom is going to increase the normal force. So to figure out what the normal force is, to figure out by how much the normal force changes, whether it's increasing, decreasing, or remaining the same, I need to compare these two and figure out which one's bigger. Okay? So let's do this one first. Let's figure out the weight of the sand in free fall, because that's going to be subtracted from the normal force. The weight of the sand in free fall, I'm going to make two assumptions of variables that we're going to need. First of all, it's something we can measure if this is a real world scenario. So I'm not just like magically coming up with these numbers. I'm like, okay, if I was actually trying to solve this, I could measure the height. That's something I could get. And this one's a little trickier to measure, and maybe we could figure this out if we wanted, but we're going to say we also know the mass flow rate. And I'm writing dm over dt instead of triangle m over triangle t, delta m over delta t, because that's easier to write, and it's, you know, a little bit more accurate. There's no fancy calculus. I don't want you to get like freaked out because I'm writing dm over dt, but it's just easier. Chris?
I wouldn't be fine. Just take the time it takes for all the sand to go from one end to the other of acid sand.
Right. But this is just a ruler, so
Yeah.
relatively speaking.
Well, yeah, I guess.
Okay,
It's
so let's
like
do
an
the weight
hour.
of this. Let's do the weight of the sand. Weight of the sand is going to be mass times gravity. I need to find the mass of the weight of the sand. So I'm going to take one of my givens, my mass flow rate, and multiply it by what to get the mass? The amount of time that it is in the air. Okay? What do you think the speed of the sand is that comes out of the top? 0. It starts at the speed of 0. So I'll just use one of my kinematics equations. Let's say h equals 1/2 gt squared. We've simplified that based on the initial speed being 0. So therefore t is the square root of 2h all over g. Substitution. Cool. We just got an expression for the weight of the sand that's in the air.
Why'd you? Oh, that's how you did it. Yeah, that's fine.
Good? Yeah. Alright, let's find the amount of force being imparted onto the bottom of the hourglass because of the sand that is hitting the bottom. The impulsive force. So, the impulsive force is going to be my mass flow rate times what, guys?
Velocity.
Change in velocity.
Yeah.
Let's assume that the sand hits the bottom of the scale and stops. Okay? Let's just assume it's an inelastic, perfectly inelastic collision. It hits the bottom of the hourglass and stops. So that means dm over dt times, I need to find the final velocity. Initial velocity is 0. We need to solve for the final velocity. Yeah, let's use energy. mgh equals 1/2 mv squared. All of the potential energy here is converted to kinetic energy here. And so the final velocity is the square root of 2gh.
Doesn't the time it takes to fall change because of the level like raises?
No, because as the sand falls, the level is going up.
What do you mean?
He's saying this is raising, so height is changing. But the variables in these two equations change together.
Which ones?
H and H.
Right.
dm, d over dt. Really, I mean, like, you're talking about mass flow rate changing, as long as this is not a ginormous hourglass, the dm over dt changes don't really matter. Because like, the rate that it's hitting here is the same as the rate it's coming out.
Oh, okay.
Yeah. Okay. Yeah. Alright, so, are these the same? Which one's bigger? You can set them equal to each other, it's all the same.
Yeah.
Actually,
Or you could just, stare at it long enough and you might realize the answer.
they're the
Supposed to be
same.
one of them.
Why are they the same, Brian?
Because you can just, just factor the g back into the square root. That would be g squared times place over g.
Watch this. Let's multiply this one by root g all over root g. Right? And if you do that, you get dm all over dt times what? Root 2gh all over g times g. Look at that.
So
They're the same. So, the weight of the sand in the air is equal to the impact force of the sand near the bottom.
Whoa.
Whoa, no change.
What? Oh, okay.
The scale is
Wait, so are you trying to say that reading is good? Doesn't change now?
What do you mean now? As if I was saying something before.
It changes.
Like the answer didn't answer.
So no, that's not the force of the sand.
Oh yeah, sure, yeah. When the sand first starts to fall, how does it change in time?
It decreases
Why?
because the sand is no longer held up by the turbine.
Yeah, the amount of time it takes for the sand to fall from here, the first grain of sand at the bottom, you can see the scale decrease because no sand is hitting the bottom. And when the last grain of sand falls out of the top, you'd see it spike for as long as this column of sand is still falling to the bottom, and then it would settle back down. So, yes, Mr. Dandigar.
Uh-oh.
Rotational dynamics, let's
Hard
go.
to.
Today's not bad, don't sweat it.
Right here.
Fun tight as a fight.
Oh, you combine those two?
Every day. That's the best way. I think that's you.
that's been a past life.
Okay. So, let's talk about rotational motion. Rotational motion.
That's another book.
So, up to this point, we've only been focusing on translational motion. But in reality, things are doing a little bit of both, right? This diver is translating through the air and spinning at the same time. You can see the little water droplets are a great way of modeling inertia. We'll talk about it later because I'm on the call right now. And inertia is not really our big topic for today. But you can see lots of cool inertia by looking at the path of the water droplets on this diver. But one of the big assumptions we're going to make is that these are rigid bodies. It makes it a lot easier to solve. And the implication of a rigid body is going to show up at the very end of today, probably, in how our variables react to the motion of entire systems. On a microscopic level, smaller than microscopic, I guess, that's kind of a way of modeling the molecules, assuming that there are rigid rods between each molecule. It's kind of what we mean by a rigid body, that it's not going to flex and bend or stretch. Think about a pinwheel spinning as a rigid body in motion. You know what a pinwheel is? Like one of those things you blow on and... Like that? That's a pinwheel? That's a rigid body. And a hurricane would not be a rigid body. Right?
Obviously. Because it's a fluid.
Right. Right? A hurricane is not a rigid body, but a pinwheel is. If a hurricane was a rigid body, think about how fast the winds would be out here at the extremes.
Dang.
Right?
Oh.
But actually, the winds are more extreme here for a hurricane than they are here. It's not a rigid body, rigid body. Cool? Simple way of thinking about it. This is a good visualization of translational plus rotational motion. Things translate, rotate, things do both.
Oh.
So we're going to start out by just focusing on the rotational, since that's new. But then we're going to add the translational. This unit is kind of like a review of the entire course to date. Because we're going to do rotational kinematics, we're going to do rotational energy, we're going to do rotational forces, we're going to do rotational momentum. right? And so what you do is you kind of get to review everything, combine it with some translational stuff, and then when the last unit comes in the final exam, you're like, it's okay, I've been thinking about all of physics for the entire year, and you're not going to have hours of studying in you because it's so cumulative. I didn't say that. Okay, you can think about rotational motion as one-dimensional in a sense. If you're following a path on the rim of a wheel, it's one-dimensional motion. Imagine you're an ant. Got it? You're seeking breadcrumbs. Okay, as you crawl along the edge of this wheel, us out here in the laboratory, we look at it and go, hey, Mr. Ant, you're going in a circle. I might model your motion using polar coordinates, or I can put it in the XY axis and be like, y squared and x squared is r squared. We could model it like that, but the ant's like, no, one-dimensional motion for me. No. Right? It's kind of like if you decided to walk around the world in a straight line, you'd be like, I'm only moving in one dimension. But somebody outside of Earth watching your motion somehow would say, no, you went in a circle. That was rotational motion. But you're like, no, it's one-dimensional. So here, what I've got drawn here is S represents what? Arc length. I've got a section of this wheel labeled as the arc length. And if the wheel rolls from here to here, this much arc length touched the ground, which you can also model as a linear distance. The idea of rolling with its connections to linear motion and using arc length is going to really be important probably next week. This is the angular displacement. I won't repeat your question, Alex. This is the angular displacement, theta, so lowercase Greek letter theta. Angular displacement measured in what?
Radians.
Radians. Is radians a unit?
No.
No, it's not. Why? I don't remember. But it's not a unit. Okay. So I'll show you the mathematical implications of that in a little bit. Alex, what's your question?
This is just a comment, sort of. Like, the Georgia Tech teacher guy talked about how you can model any motion with 1D, and so they the scientists had to go through and prove that we lived in a three-dimensional world and not a one-dimensional world.
Yeah, I've seen that. That's cool. What's up? Say what? First.
Will you be here for a few minutes after school?
Yeah.
I'll come back.
Okay. Yeah, it's crazy.
Yeah.
It's cool because you can model 3D space one-dimensionally. Because you can go anywhere in 3D space along a one-dimensional path.
Yeah, so like it just wraps around the sun.
Yep.
So you have to prove that it's 3D.
You talked about that in Calc 3? Cool. Okay, so arc length, angular displacement, and radius. Think back to the good old days of pre-calculus.
No.
Yeah. And somebody tell me, how do you relate those three variables?
S equals r theta.
S equals r theta. S.
That's not. I'll explain later. What?
S equals r theta. S is measured in what? Meters. That's my arc length. R is measured in
Meters.
theta is measured in.
Radians.
That's what I meant when I said radians is in a unit.
It's like a degree.
S is not measured in meter radians, right? Rad meters.
No.
It's just measured in meters. Radians is kind of like the
Degree.
it's the non-committal unit.
You call it degrees. You call it degrees.
Yeah, you can think it's kind of like degrees. Yep. And you can kind of think about radians as like this guy that says, "Great, I didn't want to be in charge anyway. You take the ball. I'm done." Right? As soon as somebody else shows along, it disappears. So S equals r theta. Theta is, I already told you, called the what? What's theta? Angular displacement. Okay, here's the beginnings of a pattern.
Everything's angular.
Everything's angular. In our translational units, we had displacement. And here we've got angular displacement. In our translational units, we had velocity. What do you think we're going to have here?
Angular velocity. Non-angular velocity.
And what about acceleration?
Angular.
What about momentum?
Angular.
Nice. It's a pattern. Okay. So, a change in S is a change in theta times R. Now, you know calculus. Anytime you see these triangles, these deltas, what can I simplify that to?
Final minus initial.
Yeah, so let's rewrite it. If r is equal to delta s over delta theta, and I say think about it in terms of calculus, r is ds over d theta,
Oh, that's true.
right? And it should make sense. So you don't do anything out of dr, right? If I wanted to find a little piece of ds here, some ds, it's not going to be dr ds d theta, right? Because r is a constant. It's the radius, right? It's a distance from the axis of rotation to here. And if you want a little piece of the arc length, you're only going to do a little piece of the angular displacement. And you're not going to say, oh, that means a little piece of r as well. Infinitely small piece of r. That doesn't make any sense. So it's the whole r, even though we've got a ds of d theta. Students sometimes struggle with that. Okay, let's talk about angular velocity. What's the equation? What's the fundamental equation for velocity?
dx over, or change in, the change in position divided by time.
Yeah, dx over dt. That's the fundamental definition of velocity, dx over dt. So what do you think the fundamental definition of angular velocity is?
ds over dt.
Not ds over dt, d theta over dt. Our angular velocity is d theta over dt. The change in angular displacement over time. And the variable we use to represent it is lowercase omega. This is omega, not w. This is omega. W looks like this. And this is omega.
Cursive W.
Wow.
Negative. This is omega.
And part of infinity.
Alright, well, I can come up with new names for you too. Okay, so what are the units for angular velocity? Just look at the equation and figure it out. Radians per second. Duh.
Wait, you said radians aren't really a unit, right?
Right.
So is that the same as like frequencies? Same, like this is just one over time?
Yes, actually it is.
Okay.
And we call this, for a second I was like, no, frequencies hertz, because I'm teaching sound right now in pre-AP, so
Yeah.
thinking about it in simple terms. Yes, we also call this angular frequency in the next unit.
Okay.
We already answered this. We're good. So omega is delta theta over delta t or d theta over dt. This is the average angular velocity, assuming what?
Angular acceleration is constant.
Nope.
No.
Zero angular acceleration, right? So we're just kind of playing with these ideas right now. You're like, well, I haven't seen a slide on angular acceleration yet. Why has he said the words? Because you're clever and you can figure it out. If velocity is constant at delta x over delta t, then angular velocity is constant at delta theta over delta t. As long as there's no acceleration in the first case and no angular acceleration in the second case. Got it? Angular acceleration would make this change. What do you think positive is? Clockwise or counterclockwise?
However you set the origin.
It's counterclockwise. You want to know how you can remember that?
The
Throw up your right, well, unit circle, yeah. Duh. And that's really like the more reason behind why, but we're just going to remember it. Throw up your right hand. Out of the board is positive. Remember that?
Oh, not this thing.
So take your thumb pointed out of the board,
Oh.
your fingers in a circle. Physics gang signs.
I thought you were about to say something like wax off.
That would be cool. I'll think of a way to incorporate the Karate Kid.
Like, let's say, like, for a tire, it has translational displacement and the angular displacement. So, like, if we're, like, solving a problem, are we allowed to, like, have angular and translation be two separate things?
Yes.
Two.
So when we're dealing with angular stuff, we don't get to set the pointed axes how we want to.
You do. This is just conventionality. Right, up is typically positive. Right is typically positive. Counterclockwise is typically positive. There we go. We just need to go back in time to whoever invented the first clock and be like, psst, can you make it tick the other way? We're all really curious. Okay.
5 of them?
It goes backwards.
He's got one that goes backwards.
Maybe it goes
Yeah,
forwards
and then
because
it
counterclockwise is possible.
Oh, no, it turns the other way.
Wait,
Yeah, I
but then if you make
the
the,
series guys, next one was like
if you
this.
make the clock go backwards, then
Yeah, 'cause when you
counterclockwise
look at
becomes
it,
clockwise, then clockwise becomes positive.
Yeah.
Oh, yeah. Semantics. Okay.
I'll show it to you today.
Describe this particle's angular velocity from the graph below, and then draw, everybody draw in your notes. You want good test-taking skills, good study skills, good ways to succeed, play along. Draw the angular velocity versus time graph.
The negative 2? Down here.
Oh, it's negative. You had the answer on this one in the rock board. I know.
I forgot to put the next slide too. Okay, describe the motion first. What's it doing from 0 to 3?
What's it doing at constant speed?
From 0 to 3, what's it doing?
Constant velocity.
Constant velocity, clockwise or counterclockwise? Counterclockwise, why?
Positive.
Positive slope. Then what's it doing from 3 to 5?
Going back.
Going, not decelerating, it just suddenly switch directions. Yeah, this is spinning clockwise. It's like we're spinning counterclockwise at a constant speed. And then suddenly we're like spinning the other direction. Faster or slower than this one?
Slower.
A little bit slower, why?
Less steep.
Less steep, good. What are we doing here?
Zero.
Not moving, 0. There's our graph. Where do these numbers come from? Negative 5, 2, 5.
The unit circle.
Well, okay. A little. But the slope of these lines. Yeah, the slopes of the lines give us these. Right, and we're not taking into account the fact that in the real world, it'll probably look more like this. Like that, you know? It's not going to be like sudden magical change. But it's a good model. Particle moves clockwise around a circle at a constant speed for 2 seconds. And then it reverses direction and moves counterclockwise at half the original speed until it has traveled through the same angle, the same angular displacement. That's another way of saying that. Draw the position versus time graph for the particle and then decide which of the options below best matches your answer. It's a good test-taking strategy to think about what the answer looks like before getting mired down in the bog of potential answers that the test takers have carefully created in order to confuse you. Yep.
What's the camcorder for?
The what?
Lovey.
The camcorder.
Oh, people who aren't here.
Oh, can you do that tomorrow?
Yeah.
Okay, thank you. There's a lot of questions.
$10, come on.
Say what's a robot? I read about these things called robots.
What is a robot?
Did you guys see the video of that dude last night? Who he was like, I built a robot to receive my high school diploma. I was like, whoa.
He's the one that won.
Yeah, I know. Okay, so which one is it? B, right? Clockwise is negative. We have a negative displacement, and then at a slower rate, we decelerated through the same angle, which means we ended back up the origin. This is like we're tracking a particle on a wheel. I'll get my big spinning wheel of science out tomorrow. But you can say the particle's here, and here it is going along, and then we went back to where we started. All right, this is an important conclusion. And I actually don't like it that much it's given away that fast. I should hide part of that. Let's go and just put it on the board. Okay, so the tangential velocity of a particle going in a circle. The tangential velocity is distance over time, right? We'll assume it's constant for now. So let's just say it's ds all over dt. Change in displacement all over change in time. And this is just the arc length all over the time. We have another way of writing arc length. I can say ds equals
R d theta.
r d theta. Why not dr d theta? Yeah, r is not going to change. It's the whole radius, right? So s equals r d theta. So this is the same thing as r d theta all over dt. What's d theta over dt?
Omega.
Oh man, check it out. Meters times radians per second is meters per second. Meters times meters per second. Sorry,
Meters and
meters times radians per second is meters per second. Wait.
Was that better?
Omega? Are we seeing a pattern yet? S equals r theta. V equals r omega. We've got our translational variables and our rotational variables. And what are we doing to get from translational to rotational? Just
Even
the
rotational
radius.
transition.
Yeah. Question. The picture on the left shows a rotating rod with 4 bulbs placed at regular intervals. How does the angular velocity of each bulb differ? The ones, well, just talk to the person next to you for a second. Decide. How does
The angular velocity is distributed to and it's the same time. But the translational velocity is much greater on the outside. That's because of rigid body. You want to say hi to Yeah, I've been playing with it all day because I figure I'm recording. She texted me to say hi, like just because they started.
Okay. So,
I think they're in like 4.
how do their angular velocities compare? They are all the same. Somebody raise your hand and tell me why. Hasan.
This angular velocity is just d theta times r, and they're changing the same angle. Their angle is changing the same.
Yeah, this inner bowl has swept the same angle as the outer bowl over the same period of time, right? This inner bowl didn't get here faster than the outer bowl. And the theta from here to here is the same as the theta from here to here. Alex?
I'm so sorry. This thing is awesome.
Thanks. How do their tangential velocities compare?
One's farther from the
That
center,
was-
have more.
That was the capacity.
Good. I heard some right answers in there. Joe, will you explain it for us?
The data had the lowest radius, R, and they all have the same velocity. It had the best tangential velocity.
Yeah. This one's got the biggest tangential velocity because it's got the biggest arc. You know that practically, right? My fingertips are moving faster than my ears. Right? and now I'm busy. But we kind of said that earlier about hurricanes, right? Just conceptually, you know that a hurricane would be very destructive if it was a rigid body and talking like David and Paul are. Okay, that's what we just said. Now, until this point, we've done exclusively uniform circular motion. We're going to move on. We're going to do motion that's not uniform. No, it'll still be a circle. Still circular. If I have an acceleration, how do I calculate the angular acceleration, do you think? First of all, what do you think the units are for angular acceleration? Take a guess. The units.
Per second squared.
Radians per second squared. Does that make sense?
Yeah.
So angular acceleration, I expect the units to be radians per second squared. How do you think we calculate it?
Omega over t.
Yeah. How did you calculate acceleration? What is the equation for acceleration?
dVdt.
Yeah, dv dt, right? Acceleration is dv all over dt. So what do you think angular acceleration is?
d omega over dt.
d omega over dt. Or if we assume a constant angular acceleration, or if we look at the average, delta omega over delta t. You know what the variable is for angular acceleration?
Not a clue.
No, good guess.
Radian.
Alpha. Lowercase alpha. Looks like a fish, but it's not fish, it's alpha. Some people have a lot of trouble drawing this one. People are like, this one's tricky, maybe I should do it like this? I feel like you need a Demelian course in Greek to do a physics class. Let me give you help. I personally usually start right here on the upper end and then loop like that. That's how I do my alpha. That's angular acceleration in radians per second squared. Let's do a quick comment on what causes angular acceleration. If we're looking at the slides, if I have angular acceleration, my omega is changing. Therefore, my tangential velocity is changing. Right? Omega is tied to tangential velocity. So, here in this picture, if I have a particle going in a circle, tangential velocity until this point has been constant. Set constant velocity in a circle. And if I have some acceleration, let's give the acceleration two components, a radial and a tangential component. You guys should be comfortable with the radial and tangential axes. We did these in our circular motion unit earlier in the year. The radial dimension of acceleration, what does it do to the velocity vector?
Turns it.
It turns it. It changes its direction. The radial component of acceleration changes the direction of the velocity vector. What does the tangential component of acceleration do?
Increase the tangential velocity.
It increases it if it's pointing in the same direction.
Changes.
Decreases it if it's pointing opposite. It changes its magnitude.
Yeah.
Yeah. So, velocity is always tangent to the circle. So the radial component, Vr, is always 0. Therefore, the radial centripetal acceleration only causes the particle to change direction, not magnitude. This is kinematics stuff, right? Where we talked about how acceleration has to point the same direction as velocity to make it speed up or slow down.
Yeah.
The tangential acceleration causes the particle to change speed. And the angular velocity is the rate of change of theta. Bless you. Bless you again. Bless you. Now, which of these, the tangential acceleration or the radial acceleration, do you think ties in with angular acceleration?
Tangential.
Tangential. We have done radial acceleration already in this class. What did we call it?
The centripetal.
Yeah, so a lot of people, they come to me later and like, what is centripetal? Well, centripetal is the same thing as centripetal equals radial. Those are the same things. Centripetal acceleration is radial acceleration. And the tangential acceleration is connected to this. Take a wild guess. What's the equation for alpha in terms of the tangential acceleration.
R alpha is equal to tangential acceleration.
Have you seen the pattern yet? S equals R theta, V equals R omega, A equals R alpha. And this is tangential, tangential, arc length is tangential. So good. Hey, speaking of centripetal, can you put the centripetal acceleration in terms of omega?
Probably.
Do that. Put the centripetal acceleration in terms of omega. Omega and radius. Put it in terms of omega and radius. Write the equation for centripetal acceleration that you learned weeks ago, or maybe months ago, or maybe last year. And write that in terms of the angular velocity, omega. What's up? Are they all gonna look like what?
Omega squared is
That's capital omega. This is a capital omega.
Lowercase omega is like the W of squared.
This is lowercase.
Huh?
Okay, you should get this. The centripetal acceleration is omega squared r.
Yes.
Woo! So there is a connection, right? Another way of thinking about that is the faster something is spinning, the more centripetal acceleration you need to keep it going in a circle. That's kind of what that equation says. The faster something is spinning, the more centripetal acceleration you need to keep it going in a circle. That's what that equation says.
Wait.
The faster something is going, omega, the more angular speed it's got, the more centripetal acceleration has to fight the inertia of the object going in a circle.
So as omega gets bigger, centripetal acceleration gets bigger.
Yeah, it's a direct relationship with an exponential. Okay, let's combine these guys. And actually, you know what? I don't want you to write this down. I want you to just look. Okay? What this series of equations does is it shows you kind of why. You know what? I don't think these are practical enough. How about this? If you want to go back and look at my notes later online, this slide will describe the justification.
There it is. There's the good stuff.
The justification for the tangential components of velocity, acceleration, and displacement in terms of our original kinematics equations from the beginning of January. It's kind of like why we are in 1D motion. Chris?
So is there like a perfect angle towards the inside of a circle where you can have an acceleration point and maintain certain radius, like in circular motion, where the tangential...
Yeah, I'm sure there is.
Okay.
They have to both be increasing the same amount together, so probably 45 degrees,
Okay,
because then it's root 2.
yeah.
Alright, we already said this. Angular acceleration is the slope of the omega versus t curve, the angular velocity versus time curve. The area under the angular acceleration versus time curve is angular velocity. Yay, calculus. Now, watch this. This is the last thing we'll do today. If, let's assume a constant